Risk-neutral pricing. This is conceptually the most important set of slides in the course. This is the main kind of economic idea behind the option pricing theory. So let's see what this means and how it works. Well, pricing of random payoffs has existed for a long time, like a century or longer, in insurance industry. Okay? And in insurance industry, the way it has been priced is basically like this. Suppose this is a value of your insurance claim as a random payoff. Maybe it's the payoff the insurance company has to pay if your house burns down. Okay? So it's modeled as some random variable. The insurance company has a model for the probability of your house burning down and how much it would cost to pay you the insurance. Then if this wasn't random, you would just discount it and to get the present value. But if it is random, you can take expected value. Okay? And I'm using here expected value with a subscript t, meaning that this is expected value given the information that I have at time t. It's conditional expected value, conditional on the information at time t. So this is the notation. And that would be the value that in principle the insurance company should charge you, would charge you today. C of t would be the price of that insurance for you in kind of a fair price. Okay, the insurance company may want to charge a bit more than this because they want to make some money, not just be at zero profit loss. And the idea here is that they are in a business of selling a lot of insurance claims, thousands of them, and they're basically just doing the law of large numbers, right? They are estimating that the actual value per claim is going to be close to its expected, to its theoretical expectation. Okay? So the average value of a claim they have to pay is the actual average is going to be close to the theoretical average, to the expected value, if their model is correct. Right? So that's why this is the way traditional insurance would price insurance claims. Okay? Turns out this is not quite how this is going to work for options. It will look very similar. Let me just preview what's going to happen and then we'll try to explain it. Except I'm not going to use this expectation. I'm going to change this expectation. I'm going to use either Q here or a star. There are two different notations, or a star. In the textbook that I wrote, we use star, but more traditional notation is Q. So I'm going to change. I'm going to average. I'm going to take expected theoretical expectation of my discounted future payoff, which is going to be an option or whatever, but not under the actual probabilities that I believe are real probabilities, but under some artificial probabilities, Q or P star. Okay? So I'm going to change my model. I'm going to change the probabilities in my model, pretending they are real probabilities, but they will not be real probabilities, and then I'm going to do expected value under those probabilities. And this is completely mysterious at this moment if you haven't seen this before, but we will try to explain why this happens. Okay? So it's different in financial pricing as opposed to insurance pricing. All right, so let's see a little bit why this cannot work in financial markets. So one particular claim that you may want to price is simply a stock. Right? A stock is, you can think of a stock as a call option with zero strike price. So let me, instead of C of t, put S of t for a stock. Okay? So if this formula was correct, if this is correct, then I would have that I moved this e to the minus r minus t, which is to the other side. I multiplied by e to the minus rt. So I moved this small t in the exponent and moved it to the other side. So if this was correct, it would mean that the discounted stock price today is equal to the conditional expectation of the discounted stock price in the future. Okay. So on average, if this was correct under the actual model probabilities, on average, my discounted stock price would never change. And in fact, it would behave on average as the bank account, because I'm discounting by the risk-free rate. Now, in reality, there is no reason why that should be true. In fact, if it was true, the stock market would not exist, because if the stocks were on average returning the same as the risk-free instrument, why would you invest in stocks? They are risky, but on average they give you the same as the non-risky, risk-free instrument. So typically, at least let's say for a US index or most stocks, you would expect the expected value to be higher in the future and not equal to today's stock price. So that's intuitively why this type of pricing cannot hold in reality for all, at least not for all stocks. Now, if this does hold, we have a name for this property. So if the today's value is equal to the expected at time t expected value of the future, and if this is true for every small t and every capital T, we say that such process is a Martingale. Okay? So if I denote by m of t, the discounted stock price process, I can write this as m of t, m today, is equal to the expected value from the point of view of today of the future value of m. Okay? This is called the Martingale property. The process which satisfies this is called the Martingale process. It's just a terminology from probability theory, stochastic processes. It's very useful, as we will see in option pricing. Okay? So this last line is the definition of a Martingale property for a process. In terms of gambling, if you think of this as gambling, winnings and losses, this would be a fair gamble. Right? A Martingale would be a fair gamble, which on average you neither lose nor win. Or in terms of estimation, if you think of expected value of the future as your best estimate of what's going to happen, then your best estimate of what's going to happen in the future is in fact what you see today. You just say my best estimate of the future value of m is today's value, what I see now. So that would be a Martingale process. Stocks are not typically going to be, discounted stocks are not going to be typically Martingales under actual probabilities, but we will change probabilities to make them Martingales. And because, you know, if I really want to price like this, if it's indeed true that I can price like this, but with the expectation, but maybe under some other probability, that means that stocks in particular have to satisfy this under some other probability. Okay, let's make this more clear now. I'm just jumping ahead too much. All right, so here it was just kind of intuition, what is insurance pricing, and there is a Martingale property, and we'll see how we use that. So this is what we are going to do. We are going to look for probabilities under which discounted stock price is a Martingale, which can be written in symbols like this: probability Q or probability P star, and then I just put a star here. So the expectation of the future, discounted future, is equal to discounted today's value for every lowercase t, for every capital T. Okay? If I can find such a probability Q or P star, whatever you want to call it, those probabilities are called Martingale probabilities, or risk-neutral probabilities, or pricing probabilities. Three names. Okay? Martingale, risk-neutral, pricing probabilities. The Martingale because comes from the stochastic processes terminology. Pricing probabilities because in fact it turns out that this is how we are going to price everything, not just stocks. We are going to get prices of everything doing this. Risk neutral, roughly speaking, because, well, this is not quite correct, but let's say roughly speaking because it makes the stock behave on average as the risk-free instrument. That's not quite correct, but let's just stay with that. This is a risk neutral terminology. All right? So I will be denoting in a discrete time model those probabilities with qi or pi star, lowercase pi star. All right, that's just a definition of what a Martingale probability is. So this is what we hope for or expect to have. Under Martingale probability, if I put S of t here, this would be correct. If I put S instead of capital C for pricing stocks, it would be correct. I again moved now e to the RT to this side, small t. So the hope is that this is going to be true for every random payoff which pays something at capital T, which is known at capital T. Okay? So C of capital T, this stands for a contingent claim, let's say, or just a contract payoff. Contingent claim is just a general name for random payoffs. Okay? So this is what we hope to have. We hope to have that price of a claim today, which is denoted C of small t, is expected value under Q of the claim's discounted future payoff, which is the right-hand side, the expected value at time today. Okay? So, well, it looks like this if we have a continuously compounded risk-free rate, which is constant, but it might be some other discounting, whatever you use for discounting. And C of t is like a European type option. It's something which is paid at capital T. Okay? So what we want to do is to justify this formula. And the questions that arise here are which Q, how to find it, are there such Qs, are there Martingale probabilities, and how many are there? Is there one or are there more? Okay? So these are the questions that we want to answer. It will, in fact, be the case that this formula is correct, but let's see why. Okay, before I explain why, I'm going to do single period binomial model option pricing. Okay? That's the easiest possible example. Let's take some numbers. Let me take R. Maybe this is a short interval, so it's a low interest rate during the period, 0.005. The stock starts at 100, goes up to 101, goes down to 99. Okay? And I want to price a European call option here with a strike price equal to 100. Okay? It's a call option. And let's assume that this is a model I believe in. If this was the correct model, what the price, of course it's not a correct model, it's oversimplified, but let's compute the price assuming this is the model for the stock. Okay? So the payoff of the option is going to be $1 if the stock goes up and $0 if the stock goes down, because it's 101 minus 100, that's 1. 99 minus 100 is negative, so it's zero payoff. The option is out of the money. So I'm going to price this not by using, right now, forget about Martingale probabilities. I'm going to price this the way I know how to price things. I'm going to try to see whether I can replicate the portfolio of $1 and $0, whether I can replicate this by trading in the stock and the bank account. Okay? So in other words, I'm going to try to see whether I can replicate a payoff of an option, of the option here, by trading in the underlying assets. And if I can do that, then I'm going to use the law of one price, which says if I can create one payoff in two different ways, the price has to be, the cost of doing that has to be the same, which means buying this as an option or investing in the money in the bank account and in the stock, whatever money I need to invest to replicate this option's payoff, that money has to be the price of the option. Okay? The law of one price, I can create the same payoff two different ways, either by buying an option or by trading in underlying assets. The cost of these two things should be the same. That's going to give me the option price. Okay? Let's see how this works here with numbers. Replicating 1 and 0, if the stock goes up, it has to be $1. Money in the bank is the same. Money in the bank in the future is going to be initial money in the bank, delta 0 times 1 plus the interest rate, both here and here. And then if the stock goes up, I'm going to have delta 1, that's the number of shares in the stock, 101. If the stock goes down, I'm going to have delta 1 times 99. Okay? When it goes up, it has to be 1. When it goes down, I want it to be 0. Okay? So you can think here from the perspective of the seller of the option, who needs to pay $1 if the stock goes up and $0 if the stock goes down. And he wants to trade, hedge in the bank and in the stock in such a way that he has exactly $1 if the stock goes up and exactly $0 if the stock goes down. And then he would try to do this replication. Well, this can be solved. It's a two equations in two unknowns, delta 0 and delta 1. So it will, in fact, it can be solved for any option, not just the call option here and 1 and 0. In principle, it can be solved for any option. We say that such a model is complete. I'll talk about completeness later. But it can be done. And this is where it helps that it's a binomial tree and not a trinomial tree, where you will have 3 equations with 2 unknowns. So it's actually important that we only have 2 possible values in the future. Okay, so I solve this, and I get minus 49,254 in the bank and 0.5 in the stock. What does this mean? If I want to replicate this payoff, maybe as if I'm the seller of the option, I want to buy half a share of the stock, and I will borrow 49,254. But borrowing 49,254 is not enough to buy one share or half a share of the stock. Half a share is $50, right? Because the stock is 100. So half a share is 50, and I'm only borrowing 99,254. The difference is the cost of establishing this portfolio, the cost of the replicating portfolio. Okay? The difference of 50 minus 49,254 is the cost of the replicating portfolio, and I claim this, if I don't want arbitrage, this should be the price of the option by the law of one price. Okay? So the same logic we used before with deterministic payoffs. If I can replicate a payoff, then the cost of replication should be its price. And here in this model, I can replicate the payoff of the option, 1 or 0, by using this strategy, buying half a share of the stock and borrowing 49,254. So I claim that's the price, and the price is the difference, the cost of that portfolio. Call it C of 0, or C of small t, whatever. So it's 50 minus 49,254, 0.746. Okay. Let's just check numerically. We basically know how to construct arbitrage here by cheap sell expensive. Let's just check that this is the only no arbitrage price in this model. Okay? So if we agree on this model, we should agree, if you are a buyer and I'm the seller, we should agree this is the price. Of course, in practice, people will have different models and might disagree, and they will trade. Actually, theoretically, in this model, you don't even need options. They are redundant, because you can just create options by trading in the stock and the bank account. Now, in practice, this may be difficult, especially when if you believe that a continuous time model is more correct, or multi-period model, then you will have to trade a lot, or even continuously, to replicate an option. So that would be complicated, and it's easier to buy an option just rather than to trade. But theoretically, in these type of models, which are called complete models, options are actually redundant. They don't have a reason to exist, because in principle, under our theoretical assumptions, you can just create option payoffs by trading in the underlying assets. All right, going back to the just checking that this is the no arbitrage price. Let's first suppose that the price is higher. Let's say it's $1 instead of 0.746, and well, sell it if it's high, right? If it's expensive, sell it. I sell it for 1. I have 1 minus 0.746. Maybe I invest in the bank or whatever, put it under the pillow. It's going to be arbitrage profits, because I can use the remaining 0.746 to set up exactly the portfolio from the previous slide, and I will have $1 if the stock goes up, I will have $0 if the stock goes down, and which means I will be able to pay the option payoff when it's exercised, if it's exercised at the end, and I have 0 profit losses in the future, and I still have 1 minus 0.746 initially. So positive profit. I say arbitrage here, but I still don't know it's arbitrage. I have to check. Oh yeah, I'm sorry, here it's arbitrage. No matter what happens, whether the stock goes up or down, I'm fine, and I have positive profit. Okay, it's similar. If the price is lower, you just do opposite positions. So let's say the price is just 50 cents, 0.5. Buy it. It's cheap. You buy it. And then you instead of buying half a share, you sell short half a share for 50. You get 50. I'm claiming that if you invest 50 minus the price, 49,254 in the bank, you'll be okay in the future, and you will still have extra profit of 0.246 today. Okay? If you do that, if you invest 49,254 at the risk-free rate, if the stock goes up, you will exercise the option, and you will get 1 from the option, 101 minus 100, you will get 1. And actually, if you see how much money in the bank you have, which is 49,254 times 1.05 plus $1, you will see that that's exactly equal to 1 over 2, which is how much you have to pay to close your short position in the stock. And if the stock goes down, you get 0 from the option, but then you can check that 49,254 times 1.05 is exactly equal to 99 over 2, which is now, when the stock went down, enough to close your short position again. Okay, so stock goes up, you're okay. Stock goes down, you're okay in the future, and you still have extra 0.246 from the beginning. Arbitrage again. Okay, so this is the only price. Cost of replication is the only price at which there is no arbitrage if this model is correct.